This is a video on the rational zeros theorem. So recall a rational number has the form p over q, where p and q are positive or negative whole numbers. So to give you a few examples, something like 7/9, negative 1.53, or 0.833 repeating, those are all good rational numbers. So like repeating decimals, decimals that stop, whole numbers themselves, or just regular fractions like you like. Something like square root of 2 or pi, those are not rational numbers. So what are we looking to do now? We are looking for, if we've got a polynomial, and remember a polynomial has this form, just a bunch of nice powers of x that are added together, and I'm always going to write it in a way so that the biggest power is first, and then it just decreases as I go to the right. Maybe remember too, we call that the leading term, and we'll call this the constant term. If I've got this thing, I want to know how to factor, find its x-intercepts. In other words, find the zeros of that function. Well, how do I find any nice rational numbers p over q that are zeros of this thing? And so there's this nice theorem from I think the 1700s about how to do that. So if something like p over q is a zero of this polynomial, it turns out that this p and this q are related to some of the coefficients that you see in your polynomial. So the thing you need to know is that p has to divide the constant, and that's what this says here. And then similarly, q has to divide the leading coefficient, and so that's what this says here. So that is what we're going to do to make a list of what are the possible nice fractions that could be a zero of a polynomial. So to give you an example here, we're going to list the possible rational zeros of 2x cubed plus 3x minus 6. So what are we looking for? We're looking for a fraction p over q so that f of p over q should spit out 0. When you plug p over q in for the x's that you see, it should make this 0, and so that should give you an x-intercept. So by the above, p needs to divide the constant negative 6. So think about what are all the possible numbers that divide negative 6? Well, you would tell me plus or minus 1, plus or minus 2, plus or minus 3, and I forgot plus or minus negative 6. So go add that in here. It's going to delete it in a second, but we'll just keep that right there. So, and then I need to tell you about what are the possible q's. Well, q's have to divide 2. And what are the possible things that divide 2? Just plus or minus 1 and plus or minus 2. And so I'll write those in here. And so q should be that. And so what should we do? If I take all the possible ones here, again, I need to add in, do I need to add it in? I guess maybe I should. Plus or minus 6 over plus or minus 1. Well, that would just be, so 6 is 1 also. And then plus or minus 6 over plus or minus 2, which would be this. So what's my point? I'm just taking, and again, pretend it keeps deleting itself. What are we doing? We're going to take all possible p over q from this list. So this is where I'm getting plus or minus 1 from. This is where I'm getting plus or minus a half from. So I'm just asking you, take all possible p over q here and make a list out of those. And I think it should be these. So what are we going to do with this? What are we going to do? We're going to do this example. I'm supposed to solve this equation. In other words, find the zeros of this polynomial function, or in other words, find the x-intercepts of this polynomial function. So to do that, what we're going to look for is, are there any rational zeros to this thing? And so I'm going to try to list them. What are they? The p's over q's. And what we need to identify or pay attention to is remember that p has to divide this negative 72, where q has to divide the 1 that's secretly in front of there. That's the leading coefficient. So if I write those numbers for p down, 72 has got a whole lot of factors. It should be all of these. So there's a lot of possibilities for what p could be. Luckily though, there's only 2 possibilities for q, because q has to divide that leading coefficient 1. So if I think about making all possible p over q, I'm just dividing by 1, right? So really my list of p over q's is just the list of p's there. Hope that makes sense. That's step 1. Now, it won't always be the case that your list of possible p over q's are this big. This is kind of a bad or extreme example. It's a good example because it's complicated. But what do? We've got this list now. What you're going to do is you're going to start just picking out of that list and trying to do synthetic division with that number you pick and the coefficients in your polynomial. And what you're looking for is you want to pick a number out of this list here that'll give you a remainder of 0. And so I'm going to try negative 2, right? Negative 2 is on my list. I see it right there. So I'm going to do synthetic division with negative 2, where these coefficients, remember they come from my polynomial up here. And I didn't randomly pick it. I kind of tried to eyeball it to pick a good number. So maybe if I'm looking at this here, if I plug in 1 or negative 1 for these x's, that's not going to make negative 72 go away. So that's kind of helping maybe where you could start with this. So that's what kind of helped me to try to pick negative 2, to apply some logic to it. But this is good. When I divide by negative 2 here, I see that I get 0 as a remainder. So now we need to put this together. What does this say? Well, this actually tells me, this information here and here tells me how to factor this original polynomial. It tells me that x plus 2 is a factor since the remainder is 0. And then what's left over when you factor x plus 2 off? Well, the quotient's left over, and that's x squared minus 5x minus 36. So now we're ready to move on to the next step. You would repeat that step. You'd go back to this list of your p over q's, which again, since q is nice, my list is really just here, and you'd pick again. Now it's possible negative 2 might work again, who knows, but you just pick again and you keep dividing. And what I hope that you see is when you do synthetic division and you're dividing, you keep breaking off one piece at a time of this big polynomial, and you get something that's maybe 1 degree less than what you started with. So eventually this process should stop. On the other hand though, sometimes these problems are a little bit easier. You're left with this quadratic right here. And we have a lot of tools at our disposal to factor quadratics. So that's why I say repeat that step with synthetic division until you get a quadratic left over. Hey, which we do right there. We're pretty happy. The next thing that you do is look at this quadratic, see if it factors, and if it doesn't factor, then try the quadratic formula. Maybe you'll get some complex answers. Maybe your answers have some nasty square roots that don't break down. But in this case, if I try to factor x squared minus 5x minus 36, I need two numbers that multiply to negative 36 and add to negative 5. That's where I'm using minus 9 and positive 4. So that piece factors as these guys here, x minus 9, x plus 4. And what do you have then? Well, you factored this entire big polynomial now. So the synthetic division, again, was just to kind of break this thing down one piece at a time until you have something left that's more manageable. So that was the only time we used the rational zeros theorem. Now, if you're asked to find the zeros, now you can read them all from here. The first one says negative 2 is a 0, the middle one says 9 is a 0, and the last one says negative 4 is a 0.